of the Bowman.
Go ahead.
Yeah. Thank you. I am Marshall Kern. I'm the president of the Bowman Center for Sustainable Energy. The Bowman Center has been around for a dozen years. We are a federally incorporated nonprofit corporation with approximately 22 volunteer associates who have lived and worked across Canada. Our office is here in Sarnia, Ontario, which is on the traditional territories of the Three Fires Confederacy. And so we acknowledge that with due reverence and respect for the First Nations of our land, that we are on their territory. This session is being recorded, and I'm grateful to Vice President Don Greaves for coordinating the technical stuff. A reminder to everybody that you are on mute, and that if you have a question, please enter that in the chat function. We will collect the questions and ask them at the end of the presentation. Right now, I'm very pleased to be able to ask Ken Darlington of Ultra Safe Nuclear Reactors program to please take over now and enlighten us about small modular reactors in Canada.
I'll do my best, Marshall. Thank you very much, and thank you so much to the Bowman Center for the opportunity to present to you guys today. It's a great opportunity for us, and you know, when it comes to small modular reactors, this is something that's, you know, coming down the road in the next 5 to 10 years, and really it's about sharing information so industries and communities can understand, you know, where we're at, and you know, what is it and when is it going to happen, and you know, where does Canada sit in all of this. So Ken Darlington, I'm Vice President of Corporate Development at Ultra Safe Nuclear. Full disclosure, I'm actually come from the mining industry. I worked in mining for about 25 years in engineering and construction before joining Ultra Safe Nuclear. And really, the purpose of that was to build a bridge between the right. So I'll move on here. This actually on our cover page here, and I'm going to be speaking about, you know, SMRs in general, not just about our technology, but obviously, you know, our technology is an easy reference point for me, because that's the one I'm most familiar with and that I've been working with for the last couple of years, and engaging with remote mines and communities and industry in Canada to talk about the potential application of this smaller scale nuclear technology. Quickly, just a little bit about the company, where I'm coming from. So it's a 10-year-old privately funded company. It's actually over $150 million US investment to date, which includes strategic investors as well as project delivery partners. We're based in Seattle corporately, and our Canadian office is headquartered in Ottawa. We're partnered with Ontario Power Generation on Canada's most advanced micromodular reactor project, and I'll differentiate between a micro and a small in a couple of minutes. Our technology, the micromodular reactor, specifically designed for remote mines, communities, and industry, a smaller amount of energy and heat for their operations. Speaking, so small modular reactors, or SMRs, generally considered to be projects that can deliver 300 megawatts of electricity and less. It's important to point out that a nuclear reactor does not generate electricity, it generates heat. So you can use that heat to generate electricity. And when we're talking about these larger scales, 300 megawatts electric, that's really talking about grid scale or very high heat requirements for process industrial heat. And then you get down to the smaller scale on the electrical side, more intended for off-grid and to be competitive fossil fuel generation like diesel, and for heat applications that need a little bit less than you know, the bigger scale ones. Gen 4 is what you'll often hear when they're talking about small modular reactors. And what that means is the next generation, we're talking post-CANDU. It's modular. The whole notion is repeatability of design and a fleet approach to manufacturing the reactors and deploying them rather than large, one-off reactors like you would see, at Pickering and Bruce and Darlington. So what's Canada doing about it? So there's been federal support for SMRs for several years now. Despite its noticeable absence in some of the federal budgets, the word nuclear is actually starting to show up. But behind all that, there's the SMR Action Plan, which started as the SMR Roadmap and attracted members from all across Canada and partners, including provinces and territories. There's an Indigenous Advisory Council to Canada's SMR Action Plan. The utilities are members, supply chain, academia, labor unions, and municipalities as well. Says 119 here. I'm sure it's probably more at this point. And this is all under Natural Resources Canada. So it's really the government collaboration to enable the advancement of SMR industries for Canada as part of its net zero by 2050 goals. And I will share this presentation, and at the end of the presentation, there'll be some links where you can check out stuff. Recently, four of the big utilities in Canada, SaskPower, New Brunswick Power, Bruce Power, and Ontario Power Generation, in March of 2021, put together a feasibility study looking at the different streams of SMRs, being grid scale, smaller scale, and industrial process heat. In addition, Ontario, New Brunswick, Saskatchewan, and Alberta signed an MOU to collaborate in the advancement of SMRs in their respective provinces. Saskatchewan and Alberta, of course, don't have operating, commercial nuclear reactors like Ontario and New Brunswick do. So there's a synergy there, and Ontario Power Generation is quite involved with Saskatchewan and Alberta and their ambitions, to get their grids off of fossil fuel, but also to provide process heat to industry such as the oil sands. What the study found is that SMRs do have the potential to be an economically competitive source of energy and provide significant reduction in carbon emissions and potential reduction in energy costs for off-grid mines and communities, dependent on the cost of diesel. And I'll talk a little bit about that in a few minutes. So in 2020, Global First Power was formed between USNC and Ontario Power Generation after collaborating for several years, and it is purpose is for the Chalk River MMR projects at Canadian Nuclear Laboratories in Chalk River. This is currently the first and only SMR project in Canada to be in formal licensing with the Canadian Nuclear Safety Commission. And it's on track to be commissioned in 2026 and commercial operations in 2027. So this is really the catalyst. I want to stress it's not a pilot plant. It's a commercial demonstration. So the design of the reactor is the design that would go into commercial application. And what that means is when you're looking at other projects from a licensing perspective, it becomes more about project-specific matters versus a new technology or a new design going through that regulatory process again. So that brings efficiency into the licensing process and hopefully cut down on the amount of time it takes to deploy these, because as you know, nuclear does have a bit of a legacy of taking a long time to get projects deployed. So that's the idea, to serve as a blueprint, demonstrate the constructability, demonstrate the safety, demonstrate the functioning, and demonstrating what you can do with the heat. Continued community and Indigenous engagements, and I appreciate sharing the acknowledgement at the beginning of the discussion, because there is no SMR project that could happen in Canada without meaningful Indigenous engagement. It has to be early, it has to be frequent. In fact, I just returned from a week in Nunavut last week, speaking to the people up there and learning about their concerns and talking a little bit about what nuclear energy could mean for remote communities in the north. It has to happen early, it has to happen often, and it has to include meaningful participation. And what that probably means in a lot of cases is equity participation. A little bit about how the reactor works. So that it's a small reactor in our case. We call it a nuclear battery. It's about the size of a tanker truck for a single one, and that produces 15 megawatts of thermal heat, which is enough to generate 5 megawatts of electricity, or a combination of process heat and electricity. Now, if you want more, you can stack them. You know, if you need 50 megawatts of electricity, you can put 10. If you need 20, you put 4, etc. It's a helium-cooled reactor. It does not need water to cool. It's cooled with the helium, and then the helium transfers the heat to a molten salt loop. And it's the molten salt that then is put into application on the adjacent plant side to use the heat for whatever you may need it for. What that does is it separates the nuclear plant in terms of what will be licensed by the federal nuclear regulator, and the adjacent plant, which is mostly a conventional plant that would have conventional steam generation, and if you're generating electricity, your steam turbines and so on. Again, air cooled. The whole idea here is for these to be deployed anywhere in the country without having to tap into a water source. The reactor runs for 20 years without refueling. So you don't have fuel coming in and out. You don't have the logistical risk of say, diesel fuel in a remote location, prone to the costs, the uncertain costs that come with using fossil fuels in terms of cost of the fuel and transportation logistics and so on. So, you're really getting cost certainty on your energy for 20 years, which is pretty amazing. This is just another depiction of the same thing, pretty much. Specifically looking at process heat generation. You produce high quality steam at 540 C, of course. You can have different types of steam for different industrial processes depending on your needs, but that's what you'd get at the high end. Availability of over 90%, and it's small and it's easy to connect into existing plants to convert. A little bit more of a depiction of what this looks like, and again, this picture is contemplating electrical generation. It would probably be a simpler adjacent plant if you were just making steam, but what this represents is a 2-reactor configuration, so to produce 10 megawatts of electricity. On the left-hand side, those 2 buildings, those are the reactor buildings, and you can see it's all modular. And those buildings are about the size of a squash court, so the footprint is quite small. The reactors themselves are subsurface. The reason for that is because the regulator is urging safety and security, which is very important if we're contemplating having SMRs being deployed across the country. So this design is, it's designed to withstand an aircraft impact, essentially. So it's more of a safety feature than a necessary practical feature of the reactor. So comparing the land use, and as I do this, I want to point out that I don't think that SMRs are in competition with renewables. I think that we need to use every tool in the box to fight carbon change, be it nuclear, wind, solar, carbon capture, anything we can possibly do. The reality is, however, we need very high amounts of baseload energy for electricity and industrial processes in Canadian industry. So you reach a point where it becomes impractical, the land use and the materials use, and the end of life on some of the renewables. So we really see it as being something that can work as a hybrid with a very low footprint in terms of the nuclear plant, and then you can complement that with renewables. What does it mean for mitigation of carbon emissions? Talking about one single reactor running for 20 years, doesn't emit any carbon, displaces 200 million liters of diesel, 245 million meters cubed of natural gas, equating to 500,000 tons or more of carbon emissions mitigated. And again, this is a unit that's the size of a tanker truck. So the power density of nuclear fuel is really quite remarkable in terms of what it can deliver. Talking about hybrids, again, no matter what people say, you can only get so far with renewables and battery storage, depending on what your applications are. However, it's great technology, and it's a way to mitigate the waste from other methods of power generation like nuclear. So an SMR can provide reliable baseload energy while still having wind and solar in the mix. That can also help with meeting peak demands. A lot of remote applications in particular, it's not always a steady demand, so you need to have that flexibility. I'll talk a little bit about the fuel, because this is one of the areas that's a paradigm shift in terms of nuclear safety. When people hear about nuclear power, they think of the three-eyed fish on The Simpsons, Isle Island. One feature of the bigger incidents that we have happened in the nuclear industry is that all of those reactor designs require active safety, active cooling. As an example, if you look at Fukushima, what happened there is they had diesel backup to run the pumps, and when they had a power failure and the cooling of the reactor failed, the diesel generators kicked in to cool the reactor, but then the tsunami came in and knocked out the diesel generation, and that's resulted in a cooling failure and a meltdown. So the idea in fourth generation nuclear is to eliminate that need for intervention to keep it safe and to let the laws of nature keep the reactor safe. So the way that's achieved is through specialized fuel and ensuring your power density is such that it can never reach dangerous temperatures. The uranium used, and everybody's probably seen the bundles of fuel rods that CANDU Reactor uses. Uses poppy seed sized pellets of enriched uranium. They're coated in several layers of material to keep the products of the nuclear fission in. The dangerous thing about nuclear fuel is, of course, the radiation, but the fission reaction produces radioactive isotopes that can contaminate material and land and the environment in general. So the idea is to keep that contained. That's what TRISO fuel does. We take those kernels and we put them in 2-inch fuel pellets in a silica carbide matrix that further enhances that no products of the nuclear fission can escape the fuel. And the density is such that the reactor can never melt down, even if you lose cooling. It reaches a temperature which is well within the safety limit of the reactor vessel, and it basically just stays at that temperature until an operator can, intervene and solve whatever the problem may be. But it's we call it walk-away safe, meaning that it doesn't have a big red button. You don't need to intervene to keep the reactor. Closure and reclamation, what happens at the end of either the fuel cycle or if the reactor is going to be decommissioned. Essentially, the fuel module can be removed and then refueled. Like any equipment, the reactor has a design life, in our case, 40 years, so you could do 2 20-year fuel cycles, and then you would have to look at replacing the reactor vessel itself, but it is refuelable. Otherwise, the whole system would be decommissioned and taken off site and returned to greenfield. The interesting thing about that is all of this is covered under the federal nuclear regulator, right up to the point where you kind of walk away from the site and leave it back to greenfield. And that has to be funded. There has to be an approved waste management plan and decommissioning plan with funds locked up to make sure that you don't have a case of an abandoned reactor or a case where the money is not there to properly manage the waste. If you don't have that, you're not putting a shovel in the ground. The project won't be licensed. So the regulatory landscape is five stages. License to prepare site is where we're at now with Ontario Power Generation on the Global First Power project. So what that means is we're doing our environmental assessment. That assessment, by the way, also partially relies on traditional Indigenous knowledge from the First Nations around where Canadian Nuclear Laboratories is located. And upon completion of that, we will be submitting, planning by the end of the year, an application for license to construct. After that, you have your license to operate, decommission, and eventually license to abandon, which means a return to greenfield. This is in Canada, but this is an interesting example of how federal and provincial / state policy is adapting. SMRs in the big scheme of things are relatively new, and there's a lot of opportunity in Alaska for remote communities and mines there to leverage this technology. However, legacy the legacy laws of Alaska prohibited any reactor smaller than 20 megawatts and only in 2 or 3 locations because it was predicated on large scale nuclear. Now they've got Canadian companies are actually involved in mining there. You've got a military base that's looking at it, and they've actually gone through the process and they've changed laws and regulations to allow reactors to be deployed. So we're starting to see this not only in the United States and other countries, but some countries are. It takes a while, to set up a nuclear regulatory framework, and we see this happening all over the world now as energy security becomes a more prominent issue. Talking a little bit about costs, and I know maybe the audience here today is more interested in process heat, perhaps, but just to kind of put it into context, again, our reactor is small. It's not intended to compete with the cost of large grid scale nuclear power generation. It's intended to compete with fossil fuels in a remote location. So you can see the 3 bars there represent a 20 megawatt, a 10 megawatt, and then compare it to diesel. We don't know what diesel's going to cost in the future. We don't know what carbon taxes are going to be for certain, depending who wins elections and so on. But what we can predict and what we can model is what it will cost for 20 years of operation of nuclear reactors and bring that cost certainty into the game, which can flip the economics on some projects as well. So the commercial model is energy as a service. While it would be possible that an end user could decide that they want to own and operate a nuclear plant, I haven't talked to any yet that aren't just interested in the energy. They would rather not have a nuclear reactor on their balance sheet because that's not their core business. They're interested in an off-taking agreement, power purchase agreement, where they benefit from that energy and it's owned and operated by an entity that is specialized in operating nuclear plants, which was part of the reason for the formation of our joint venture with Ontario Power Generation. Power Generation brings in regulatory knowledge, nuclear operations knowledge, and we, as USNC, we bring in as a reactor vendor the technology, the fuel, and so on. So that's the nature of that participation. And then each project could have other participants. including local utilities and including indigenous development corporations to bring revenue streams to those communities. A little bit about Global First Power. Again, we're in phase 2 of the Canadian Nuclear Safety Commission vendor design review, which is we're the leading SMR in that process. I already talked about our license to prepare site and bringing it into operation by 2026. The schedule. So, the question is always, how much does it cost, and when can we get one? So you're going to hear a lot of answers to that question depending on the technology that you're talking about, because it is, kind of a spectrum of technology sizes and when they'll become commercially available. In our case, we're using proven technology, and it's very mature in terms of design. That's what allows us to be able to schedule operations in the mid to late 2020s. Other designs have a little bit longer to go, and you may hear people talking about 2030s, mid 2030s, to get those. Because it can take upwards of 10 years, for all that you need to do to bring a nuclear technology into commercialization, including the community engagement, the regulatory engagement, and so on. So we're already a few years down the road. So we kind of bring the opportunity to demonstrate that nuclear power can be leveraged in an industrial process ahead of 2030, which is exciting. Okay, that's just a summary. What I would like to do now, I think we've used up half an hour. I have a 5-minute video that I will share, and that kind of give you a little bit more visuals as to how it's constructed and so on. So I will share. And I hope everybody is seeing this.
Yes, it's good.
Okay, great. Thank you.
There is no sound. Do you have the sound turned on, Ken?
There's no sound. Okay, let me just, I may need to change it from my mic to include
Share screen, there's 2 boxes, one to share video and one share sound, bottom left corner when you go to share
sound.
screen.
Gotcha. Okay. Thank you for the IT assistance. Let's try that again.
No problem.
Is that working now?
The Micro-Modular Reactor, or MMR, is a nuclear energy system for reliable energy anywhere. MMR units are used as sources of carbon-free heat in custom-designed power plants for a wide range of applications, starting from off-grid power for remote mines and communities, and extending to any power application, including industrial process heat, hydrogen production, and grid electricity. The MMR is powered by fully ceramic microencapsulated fuel, or FCM fuel. This fully ceramic core has the lowest power density of any commercial reactor ever, allowing it to safely dissipate excess heat even without active cooling. No moving parts or fluids, no operator actions, no emergencies, just simple and safe operations and power production. Helium carries heat out of the nuclear core. It is a harmless noble gas, completely unreactive and stable. The heat is stored in a molten salt thermal storage system. When power or process heat is needed, heat is extracted from the thermal storage using a steam generator. This allows the MMR to be part of hybrid nuclear renewable systems and act as a carbon-free peaker plant, providing reliable power to complement intermittent renewable supply. Ultra-safe nuclear's technology breakthroughs, protected by more than 20 patents, include the manufacture and utilization of fully ceramic cores and fail-safe reactor designs. This is the new nuclear. Ultra-safe nuclear has developed an innovative approach to manufacture and deploy the MMR that addresses the current challenges of deploying new nuclear generating capacity. Site licensing begins several years before power-up and involves analysis of environmental data and discussions and engagement with local communities. The site is prepared and civil works are executed to excavate foundations and install pilings. As the MMR is a buried reactor, a shaft is created to hold the reactor and heat exchanger. USNC has moved away from traditional construction methods, such as cast in-place concrete, to designing standard modules that are assembled on site. The power plant modules are delivered by ship, rail, truck, or aircraft once the site is fully prepared and verified. A specialized team links the modules and assembles the plant in a matter of months. Each required module for a specific MMR plant is assembled with a complete, pre-installed system housed within each module. All piping, cabling, lighting, and ducts are included in the module with specific interfaces for simplified connection of the modules during assembly. Modules include the steam generator and balance of plant equipment, as well as nuclear citadel modules like the reactor vessel and primary heat exchanger. The last modules arriving at the site are the fuel modules. After verification and testing, the MMR begins providing 15 megawatts of load-compliant thermal power for 20 years. The principal tenets of the MMR design are the application of proven nuclear technology in an innovatively small, inherently safe, simple, and affordable modular reactor design, and the use of manufacturing and deployment strategies that resolve many of the project performance issues that are currently hampering the widespread adoption of nuclear power. Ultra-Safe Nuclear was founded in 2011 and now employs over 160 staff globally, working on MMR and space nuclear power systems. The MMR is the first of our products aiming to deliver reliable energy anywhere, on Earth or in space.
Good. I hope that worked okay. Interesting on the space application as well. I mean, one of the branches of our company works with NASA developing nuclear propulsion systems for the Mars mission. So it's some pretty cool stuff. Okay. Are you guys hearing me still?
You're good.
Okay.
Do you want to share your screen again?
Yeah, I can share my screen. The presentation is over.
Oh, okay. So that's fine.
So I thought I could I'd just go back on the video here and I can have a look at these questions. My contact information, I'm happy to share with you, as well as a copy of the presentation. The low thermal efficiency is due to no cogeneration of power. You're talking about that's probably referring to the 15 megawatt thermal down to 5 megawatts electrical, which is a fairly typical loss of the heat. You could use that waste heat depending on if there's, in your industrial application, a use for it. It's fairly low. I know in mining, they look at shaft heating. You could use it for district heating as well. But it is, fairly low quality heat at that point. And they load follow, yes. So the molten salt system actually has a storage tank. There's some flexibility in how you operate the reactor. You can go less than 15 megawatt and a little bit above. The regulator would determine the where you could operate those depending on or the limits, I guess, depending on what the license application is. But generally speaking, yes. And all that happens if you run it at 80% instead of 100, it's like a battery. You use the fuel slower. So if you're running it at 80%, it'll last a little more than 20 years. And if you're operating at 110%, it'll last a little less. We do incorporate redundancy. I mean, there is maintenance and so on. So we generally do have a diesel backup, but it's a very small need because your capacity factor is not 95% or higher. But in certain circumstances, depending how many units you have installed, you may need to have some backup just to ensure you've got full reliability during maintenance. And the hybrid is the other option as well, to be able to load follow using battery storage and renewables. And depending where you are, you could also, you could have pumped storage or other means of storing excess energy when loads are low. So Global First Power would be the operator, the joint venture, but we would draw on OPG nuclear qualified operators. So it would be Global First Power, but the actual operators would be seconded from Ontario Power Generation. What temperature can the helium get to in an upset? I believe it's somewhere around the reactor. It's somewhere around 800 degrees, I believe, but I'd have to double check that with the technical guys. And then it just stabilizes at that temperature. What licensing training do plant operators require, same as full-size plants? Currently, yes. We're working closely with the regulator because everything in the regulations is predicated on large-scale nuclear, including operator training and licensing, and including licensing of the technology. And the regulator is well aware of the fact that these are much smaller, much simpler systems, and side of things, it will evolve with SMRs. They're aware of that. Kind of the first one and in the lead. So we're blazing the trail, and the idea hopefully is that will become more fit for purpose, the regulatory process. I'm not talking less rigorous, but more fit for purpose for the technologies that we're looking to license. Is the OPG joint venture just for an Ontario location? No. It's for anywhere in Canada, and certainly it could go elsewhere as well. Now, the idea would be in time, right? Like if we're deploying a project, say in Saskatchewan, Alberta, Nunavut, wherever it may be, initially, because Ontario Power Generation has personnel who are trained, the Chalk River project would be a training facility. And the idea over time is to provide opportunities for local people to get trained and to be able to operate those reactors. But at the very beginning, it's envisaged that it would be OPG personnel through the Global First Power partnership operating. Compared to the deep geological repository of conventional spent fuel rods, would be easier to potentially treat the nuclear waste from an SMR. So it would go into the same stream. Spent fuel from an SMR would go into that same deep geological repository. The spent fuel rods from CANDU are highly amenable or thought to be highly amenable to some of the recycling technologies that are being developed now. Companies like Moltex in New Brunswick, for instance, is looking at recycling of CANDU. Small modular reactors, the volume of waste is very, very small, and because it's encased in substances, it's probably a little trickier, and it's definitely not the lowest hanging fruit on the tree in terms of recycling spent fuel. We also have to consider that the spent fuel from CANDU reactors is still sitting on those sites, like from the day those reactors started in the 60s. So there's a fair amount of it. It's not a huge volume, but there's a fair amount of that, and that would be the first go-to in terms of recycling. Have you looked and have been in contact with potential locations to deploy? Yes, we have. We're engaging both with communities, oil sands companies, mining companies, and some studies have been done, preliminary siting and so. It's really about early engagement. Last week, just as an example, I was in Iqaluit and Rankin Inlet and speaking to government officials and local associations and Indigenous groups about potential locations to deploy in Nunavut, for example, which has quite a few small communities. The reality is, if you've got a few thousand people, it's amenable, but communities of 200 or 300 people, it's still a little bit too big. So those are ongoing. There's several remote mines that have been looked at. We studied the potential application of SMRs as well. And I know in the oil sands, they're getting quite far down the road and looking at the various technologies. Yeah, I think I'm at the end of the question list. If anybody else has more, please enter them in the chat and I'll do my best to answer.
What's your question?
Hi, Ken. How many jobs is this going to create, like on a given installation? And let's say it's making electricity.
So it doesn't require a lot of personnel to operate the plant. I mean, you're talking a shift size of 7 people, and they could operate up to a 10 reactor system. So obviously there would be jobs in the construction phase. You're talking a few hundred people probably during the construction, fabrication, and supply chain. But in terms of in the longer term, it's a very small complement of people to operate.
And as a follow-up?
Yeah, and so can you, to one significant figure, what would the capital cost for a system, let's say it's producing electricity? Is it like 10 million, 10 billion?
It's not 10 billion, I'm happy to say. Yeah, I mean, it's, right now it's a hard question to answer because, one hasn't been built yet, right? So Chalk River is really intended to demonstrate that. And then you're going to have learning and repeatability and all that. But we think in early commercialization, it's going to be somewhere in the $150 to $200 million range.
Question here.
Yeah, I had a follow-up regarding the number of jobs that might be generated. Sarnia here has heavy fabrication capabilities. How would you incorporate local fabricators in your supply chain, or would they not? Would the prefabricated pieces be brought up from the
Yeah, I mean, the notion is to prefabricate almost everything in modules in a module facility, like a module yard or module facility. But I would certainly think that every project will have opportunities for local businesses, and potentially, if there's, obviously there's a lot of in module fabrication, a lot of steel fab and so on. So depending on the location, I think there'd be opportunities for local small, medium businesses for sure.
Are you looking at carbon steel, stainless steels, exotics, or what kind of?
I think it's probably a bunch of different stuff. I'm not entirely versed in the materials of construction, but obviously some of the vessels and piping are going to be a little bit more exotic than just the regular, structural steel of the modules.
Thank you.
Okay, one more question here in our room.
So, yeah, you've talked a little bit about it. You said you didn't use the word consultation, but you did talk about working with Indigenous communities. What has been the I personally think nuclear has a place, but everybody doesn't. What's been the reception from society, including Indigenous people, but not are people kind of open-minded, or you got a big
Yeah, I mean, as you can imagine, it really does vary. And you're going to have those people who are anti, no matter what you tell them, right? And that's a fact of life. But our experience, including in Indigenous communities, is that people just want to understand so they can form their own opinion. What we hear a lot of the time is, I'm not for, I'm not against. I just don't understand, what's different from old nuclear, and what does this mean for my community, and what is, how do I know it's safe, right? They're open-minded. They want to learn more. And this has increased just with, the global situation today, and, energy security becoming essentially a global issue. People are wanting to hear a little bit more, and we think it's shifting a little bit in terms of people saying we need to talk more about this and we need to understand this. The project at Chalk River, that engagement plan, we have agreements with 5 different First Nations that are all kind of surrounding that area of Ontario. And just regular community consultations as well, including town halls. Our last town hall, which was it was a hybrid of in-person and virtual, I believe, had 5,000 people, including virtual, attending it. So people are really interested in hearing about it. Sometimes the naysayers are the louder voices, but most people have an open mind and they just want to understand so they can feel they're making that they have an informed opinion.
Okay, there's just a few more questions, please, Ken. There's one here in the room.
Do you want to go ahead first? Ken, you mentioned that your technology is well developed. Where was this developed? I mean, do you have a pilot plant somewhere in the States or somewhere else?
Yeah, we do. So Trisol fuel has been around for decades. There's other operating reactors that use it, and I'm not 100% sure, but I even think it's used in military applications. Our fuel, which puts it into those FCM pellets, one of those was successfully fabricated at Canadian Nuclear Laboratories, and we just opened our pilot facility for production of that fuel in BC.
Okay, there's 2 questions in the chat function.
Yeah.
What would be
So,
the TIC for a 300 megawatt installation?
Yeah, what would be the TIC for 300 megawatt installation? So if we're talking 300 megawatt electrical, that's probably outside of where our reactor would be in the market, because we're 5. So you probably wouldn't put in 60 of them. But yeah, I don't know the answer to that. I know that Ontario Power Generation is looking at the GE Hitachi SMR to install that in Darlington later in the decade. There may be some information out there as to what they think that's going to cost, but off the top of my head, I'm not sure what it would be.
Okay, and there's another question: at what carbon price does it become economic to deploy the SMR based on your estimate? Because you did share the information. 20-year cost, state stability.
So we want to be competitive regardless of what carbon pricing comes in at. So with 0% carbon tax, our models are showing that we're competitive with diesel, and that only improves if you have economy of scale, like 2, 3, 4 reactors. It gets better. So carbon pricing to us would probably just be additional, kind of an additional cost incentive to deploy an SMR.
Okay, thank you very much, Ken. I truly appreciate the effort that you and your colleagues have made to prepare this presentation and deliver it to us. Certainly, as at the Bowman Center, we've been operating, working for about the same amount of time that Ultra Safe Nuclear Corporation has been around as well. We know that, as you do, that the amount of electricity that is required in Canada to sustain our quality of life will require about triple the generation that we currently have. We know that the timelines are short, as you do as well. We know as well that we need to make sure that we aren't stranding assets across the country. We need to make sure there's proper transmission across the country as well. So we're truly grateful for the time that you have taken with your colleagues to share the information about SMRs. I know that there are additional questions people have. I'm very sure that because you're sharing this presentation and your contact information, that we will continue the discussion. And we truly wish you every success, because that will fulfill our mission as Bowman Center to be able to push forward on Canada's sustainable energy future by generating sustainable energy, sustainable jobs, and wealth creation in Canada. So with that, I thank everybody for attending. And Ken, I thank you. The last words to you, if you wish it.
Let me just jump in here. Just one, Ken, if you could just put your contact information in the chat, would be the easiest way for you to like tell everybody about that. So maybe just your email address and anything else you want to add to that would be appropriate. Thank you.
Okay. That's done, and I will send a PDF of this presentation. Can I send that to you, Dawn, and then you can distribute it to these?
Absolutely, yes. And do you mind if we put it on our website?
No, you can go ahead and do that.
Okay, good. Thank you.
Yeah. So thanks to you guys again for having us. And, you know, obviously the presentation was kind of centric on our technology, but you know, the important thing for the SMR industry in Canada, the nuclear industry in Canada, is to get one of these out of the gate. And that's what we're trying to do. And you know, that'll pave the way not only for ultra-safe nuclear's technology, but the other technologies and the other sizes of technologies as well. So really appreciate the opportunity to share some information today. I invite anybody on the call to reach out to me if they want to have a chat or would like more information. So thanks again.